Hey everyone, and welcome back to The Explainer. Today, we're unraveling a massive mystery, and I mean that literally, that's hiding in plain sight every single time you look out at the ocean. We're going to explore the invisible, almost magical physical forces that govern how absolutely gigantic, impossibly heavy objects manage to float perfectly balanced on the water. I mean, just look at a vessel like the Queen Mary 2. The dimensions we're talking about here are just staggering. From the keel all the way up to the funnel, she is 72 meters tall. But if you look closely at the waterline, only 10 meters of that incredibly massive hull actually sit below the surface. To put that in perspective, that's 62 meters of heavy steel superstructure, thousands of passengers, restaurants, and literal swimming pools towering high above the water, all supported by just a tiny, shallow fraction beneath it. So what's the deal here? It looks like it should just topple right over, doesn't it? I mean, if you try to balance a pencil on its tip, it falls instantly. So why doesn't this top-heavy skyscraper of a ship do the exact same thing? Okay, let's dive into this counterintuitive mystery of physics and set up what we call the paradox of balance. All right, moving to section 1, Archimedes and the dueling forces. To actually solve our mystery, we first need to take a quick trip way back to 212 BC. Meet Archimedes of Syracuse, pretty much the undisputed father of buoyancy. His famous principle states a really simple but profoundly important truth. The buoyancy force on a body is exactly equal and oppositely directed to the weight of the fluid that body displaces. In plain English, if you shove water out of the way, that water pushes back up on you with a force equal to its own weight. But here's the thing. Buoyancy all by itself doesn't explain stability. For that, we need to look at two dueling forces, starting with the center of gravity. You can think of the center of gravity as the single invisible point where the total weight of the entire ship, the steel, the cargo, the people, the whole shebang, acts straight downward. It's basically a force constantly pulling the object down toward the ocean floor, and its location is determined entirely by how the weight is distributed throughout the ship. On the flip side of that, we have the center of buoyancy. Remember that displaced water Archimedes was talking about? Well, the center of buoyancy is the geometric center of that specific shape of displaced water. It acts as an equivalent upward push, kind of like an anti-gravity force that perfectly mimics the exact shape of the hole the ship is carving out in the water. So you've got gravity yanking down from the ship's center of mass, and buoyancy shoving up from the center of the displaced water. When a ship is just resting perfectly flat, these two forces align flawlessly on a vertical axis. But when they don't align vertically, say if a rogue wave tilts the boat, they create what's called a moment, or torque. It instantly becomes this epic rustling match, with these two forces fighting to rotate the object back into a stable position. Which brings us to section 2, submarines and sky balloons. Now, before we fully solve the puzzle of our top-heavy surface ship, let's actually shift gears and look at fully submerged bodies. Here, these dueling forces act without the messy complication of a surface water line. And for fully submerged craft, the physics are incredibly straightforward. The rule is absolute. The center of gravity must sit directly below the center of buoyancy. For fish, blimps, or submarines, keeping the heavy parts at the bottom is literally the only way to avoid instantly flipping over. If you put a submarine's heavy engines on the roof, it would immediately roll belly up until gravity rested safely below buoyancy again. Now, what's really interesting here is how early scientists tested this out. The physics of water applies perfectly to the air, too. This right here is the great rivalry of 1783. We have the Montgolfier brothers' hot air balloon and Jacques-Charles' hydrogen balloon. Both of these relied on the exact same principles of submerged buoyancy we just talked about, but they tackled it in wildly different and honestly kind of dangerous ways. Let's look at the numbers. The Montgolfier relied on heated air, which meant they needed a massive volume, like 1,700 cubic meters, just to generate enough buoyant lift. Oh, and it carried a terrifying risk of catching on fire midair. Then, just a few days later, the Challenger took flight using hydrogen. Because hydrogen is fundamentally less dense than air, that balloon could be way smaller, just 292 cubic meters. But yeah, it carried the very real risk of just outright exploding. Still, despite their differences, both proved one big thing. As long as the heavy gondola hangs below the buoyant balloon, stability is guaranteed. Okay, on to section 3, the surface ship paradox. So heavy stuff hangs below buoyant stuff. Makes total sense, right? Well, let's bring our explainer back down to the surface of the ocean, because this brings us squarely back to our initial, glaring mystery. Here is a vessel resting calmly on the surface. But unlike a submarine or a sky balloon, a surface ship can stably float with its center of gravity located directly above its center of buoyancy. Gravity is up high, buoyancy is down low. Based on literally everything we just learned about submarines, this should be utterly impossible. It should want to flip over instantly. And that brings us to Section 4, the magic of the metacenter. Let's dive right into this and see the ultimate magic trick of marine engineering. This is the hidden geometric secret that allows a towering cruise ship to stay upright. When a stable surface ship tilts, or heels as they say in the nautical world, something incredible happens. Because it sits right on the waterline, the actual physical shape of the underwater hull changes. A wedge of displaced water on one side lifts out of the ocean, while a brand new wedge on the other side pushes down into it. Because that shape of the displaced water changes, the center of buoyancy instantly moves sideways. It slides over to literally catch the falling ship, pushing it safely back upright. But what if the ship is top-heavy and poorly designed? Well, if the center of gravity is just too high, when that ship tilts, the center of buoyancy just cannot shift far enough to the side to get underneath it. Instead of catching the fall, the two forces end up pulling in opposite directions. This creates an upsetting moment that forces the ship to completely capsize. And this brilliantly illustrates exactly how naval architects measured this critical safety margin. As the ship rocks back and forth, the upward pushing line of buoyancy keeps shifting with it. All these upward lines intersect at a single, invisible, fixed pivot point just hovering in space above the ship. This magic little point is called the metacenter, marked here with an M. Let's actually walk through this spatial sequence step by step so you can really visualize it. Step 1, a wave hits and the ship tilts slightly. Step 2, because it's at the surface, the shape of the displaced water instantly changes. A wedge of water essentially shifts from one side over to the other. Step 3, that shifting water forces the center of buoyancy to rapidly move laterally. And finally, step 4, as long as the center of gravity is low enough, this lateral shift gets right underneath the weight of the ship, generating a righting moment that pushes the ship safely back to level. It's rapid, intuitive, spatial geometry in motion. Let's wrap things up with Section 5, why stability matters. Now it's time to transition from these MIT-level physics equations to the real world, because understanding this math is quite literally a matter of life or death out on the open ocean. So the absolute crucial point you need to take away is this: the golden rule of ships. The center of gravity must remain below the metacenter. Honestly, it doesn't even matter if the center of gravity is above the center of buoyancy, as long as it stays strictly below that invisible, floating pivot point we call the metacenter. If it does, the ship will automatically self-right. But if the center of gravity rises above the metacenter, the ship is fundamentally unstable. Game over. Now, what's cool is engineers can actually tweak the distance between these 2 points, a metric called metacentric height. A huge distance between the metacenter and the center of gravity makes a ship incredibly safe, but it causes a violent, stiff, and super fast righting motion. It just snaps back upright. And you know, that would spill a whole lot of martinis on a cruise ship. So for luxury liners like the Queen Mary 2, engineers purposefully design a smaller metacentric height. This gives the ship a slow, gentle, sluggish roll, completely prioritizing passenger comfort while still keeping the math strictly in the safe zone. But what happens when the math goes wrong? Well, this brings us to the famous, real-world cautionary tale of the Flying Enterprise. Back in 1952, this freighter encountered an absolutely brutal storm. Just look at the extreme list on this vessel. Captain Henrik Kurt Carlson famously stayed on board for days as it slowly, agonizingly succumbed to the ocean. So what physically broke down here? Well, during that severe storm, the heavy cargo inside the hull broke loose and violently shifted. This physical shift in weight completely moved the ship's center of gravity way over to the port side. Because the center of gravity was no longer sitting pretty in the middle, the shifting center of buoyancy we just talked about couldn't reach far enough out to compensate. The righting arm was dangerously compromised, and eventually the ship lost its equilibrium completely and sank right to the bottom. And that, my friends, brings us to the end of our journey into the physics of floating. It is this incredibly delicate, continuous dance between gravity pulling down, buoyancy pushing up, and the ever-changing shape of the water beneath us. So the next time you board a towering ferry or a massive cruise ship, just take a moment. Will you wonder where its invisible metacenter truly lies? Thanks so much for joining me on this explainer, and as always, keep looking at the world with a curious mind.